Physics students, welcome to topic 3 in astrophysics cosmology. This is going to be a fairly short topic at higher and standard level. This presentation, this video is only going to be about 13 slides, and it's only going to be one video. So let's go ahead and get started. The first thing I'm going to talk about is something called the Big Bang model, which I'm sure you've heard of. And the Big Bang model is an effort by human beings to explain what happened about 13 or 14 billion years ago. And it says that basically the universe expanded from an extremely dense and hot state and continues to expand today. Now, the obvious question is, well, expands into what? What is beyond the known universe? Well, no one knows that, okay? And this may be an example of a piece of knowledge that we actually never ever know, but it's fun to think about it. Now, expanding means galaxies are moving farther apart from each other. Stars and galaxies are getting farther apart from each other. But it's not because they have different speeds, it's because the space between them is expanding. You can think of it as an expanding sort of canvas or a balloon, a canvas like a painting, okay? So, a car-galaxy analogy, for example. If you think of a spring as a road and the cars upon it as galaxies, okay? So the cars are like glued onto this slinky, basically, okay? As the slinky stretches, the cars get farther apart. Okay, but it's not really that the cars get farther apart. There's still the same number of coils apart, right? In terms of if your standard unit is say one slinky coil, then say the front of the green car is 1, 2, 3, 4, 5, 6 slinky coils from the front of the red car. Okay, well, it still is when you stretch it. All right, it's still the same distance apart. It's just that the actual fabric of space-time has actually changed. Okay, so again, as the spring stretches, the space between the cars increases, but it's consistent between adjacent cars. All right. So the cars are not moving, they're not increasing, the distance is not increasing because they're moving along the road. In fact, they're not even moving relative to the road. It's the wavelength of the medium, in this case the road or the slinky, or the reality that is actually increasing as it expands, and this is called the redshift. It's an increase in the wavelength of something that's moving. Okay, now to calculate the redshift, we give it the lowercase z letter, okay? If you recall from Doppler, to calculate the redshift, it's just the change in wavelength over the original wavelength. And for speeds, for very, very high speeds, a significant percentage of the speed of light, this is approximately equal to v, which is the relative velocity over the speed of light, c, okay? Try this example on your own. Okay, so I have a spectral line from galaxy A of wavelength 434 nanometers. It's redshifted to 479. What's the recession speed of galaxy A? Well, pretty simple problem. You just delta lambda over lambda equals v over c. Solve for v. Okay. The same line is from a second galaxy, is shifted from 4 to 481. Calculate its recession speed. Okay. Now, one thing that I have not yet really talked about is that if the recession velocity is greater for an object, it means that that object is farther away, and that has to do with work that Hubble did, which I'll talk in just a little bit. Okay, so because the recession speed for galaxy B is greater, then it's further away than galaxy A. Pretty interesting. All right. Now, a few more interesting things about the universe that you should know. Okay, so just after it occurred, the universe was very, very small, and its temperature was very, very hot, about 10 to the 32 Kelvin. At that stage, there were no atoms, and the density of photons was very, very high. So it was a very radiation-dominated situation. It was all electromagnetic radiation and no atomic particles. Now, all of these photons still exist, and this is the really amazing thing. They still exist, but because existence is expanding, the wavelength of those photons has gotten greater. There's been a redshift, okay, because those actual photons, their existence, what they exist in, has actually expanded, and they have become microwaves. And we know this because in the 1960s, two scientists called Penzias and Wilson, they basically mapped the entire universe, the entire night sky, and they found that it was flush with cosmic microwave background radiation. Anywhere you look, there are microwaves, and it's thought now that these CMBs, the cosmic microwave background radiation, is actually, these are actually the photons that that existed towards the beginning of the universe, and their wavelengths have gotten greater, and they have actually physically become microwaves. Isn't that amazing? You need to know that for the IB, okay? Now, after about 300,000 years, the temperature cooled way down to about 4,000 Kelvin. At that point, atoms started forming. Galaxies began forming when the universe was about 1 billion years old. And about 10 to the 10 years have actually elapsed since the Big Bang right now. It's thought that the age of the universe is between 13 and 14 billion Earth years old. Okay? All right. Now, back to the cars on springs. So the expansion of the universe can be described in terms of what's called the scale factor. We'll call it capital R. So for example, if I have two number lines here, or I have a number line starting at the very top, I have a red dot at 1 and a red dot at 3. The distance obviously between these two red points is 3 minus 2 equals 1. Now, if space expands, in other words, if the number line were to expand, if you were to pull it apart, stretch it apart like a rubber band, okay, you'd still have the red dots at 1 and 3, okay, and the difference is still 3 minus 2 equals 1, but clearly they're greater apart. They're greater than 1 unit apart, as they were in the first case, because reality for them, which is the number line, has actually expanded. So if we multiply delta x, which in this case is 1, by a scale factor, r, that will actually give the physical distance between the points. And this physical distance is given by r times delta x. Now this seems like kind of trivial, but when you're dealing with the universe expanding and dealing with big distances, this actually becomes quite an important concept. But r is really dependent on time, so it's a function r of t. This is called, to astronomers, they refer to this as the scale factor of the universe. Sometimes it's called the radius of the universe, which is misleading. It's kind of a misnomer because the universe doesn't have a shape or a size and certainly no radius, all right? Now, D equals R delta X. When a photon of cosmic microwave background radiation was emitted, it had an initial wavelength lambda naught, and lambda naught was R naught times delta X. That same photon now has wavelength lambda, and lambda is R delta X. So it turns out that the ratio of their wavelengths ends up being the ratio of the scale factors, all right? So this stretching of space is what makes it appear that things are moving away from us, all right? Now, from the redshift formula that I had before, Z equals delta lambda over lambda naught, if we substitute it into the above, we get that Z equals R over R naught minus 1. And one of the great unsolved problems in cosmology is exactly what is R of t. How does the scale factor depend on time? So if you want to win a Nobel Prize and get rich and famous and have all kinds of scientific notoriety, please figure out what R of t is. It's greatly needed in science, okay? Here's an example you can try on your own. So the peak wavelength of C and B at the moment is about 1 millimeter. In the past, there was a time when the peak wavelength corresponded to blue light, okay? Estimate the size of the universe then compared with its present size. All right, well, from lambda over lambda naught equals R over R naught, okay, we have that factor, okay? So what that means is that when the universe was mostly blue light, it was about 2,000 times smaller than it was today. Pretty interesting, huh? Now, example 3, a hydrogen line has a wavelength of 434. When received from a distant galaxy, this line is measured to be 486. Determine the size of the universe relative to its present size at the time when the light from that source was emitted. Interesting, okay? Well, we calculate the redshift being 0.12 in this case. So that means that this ratio of R over R naught is 1.12. And so what that means is that the universe was 1.12 times smaller, or 89% of its present size when that light was emitted. Isn't this incredible that we can figure this out, we think? Okay? All right, if you remember Edwin Hubble, he did a whole bunch of things with Cepheid variables, and he developed a system for determining how far away any star is by developing a system where the Cepheid variable could be sort of a standard candle in determining distance. So we've talked about that, okay? And we learned that they were related, right? Luminosity and period in that way. In 1924, he used distances to Cepheids in the Andromeda Galaxy, okay? To prove that our Milky Way is but one of a million galaxies. We've talked about this before, and that the universe is much bigger than previously thought. In 1929, he again used Cepheids to construct Hubble's Law, and that's what I'm going to talk about right now. So Hubble's Law quantizes the idea that more distant objects are receding faster. And the idea is this. If you take the ratio of the recessional velocity over the separation distance between us and the star, that ends up being constant. And that constant is called the Hubble constant. It's called h naught. And the accepted current value for h naught, which is debatable, it's anywhere between 60, 70, 75. The accepted value that we're going to use in the IB is 67.8 kilometers per second per megaparsec. Okay? And so interesting, right? So we have that as distance increases, it's, the recessional velocity of objects ends up being greater by Hubble's law. Okay? Now, in other words, V equals h naught times d. If I just rearrange this, this is actually what's given to you in your data booklet here. And T, this is also given to you in your data booklet, T is approximately equal to 1 over h naught. And I'll talk about what that T is in an example in the next, I think in the next slide, okay? All right, so number 4, use Hubble's law to estimate the distance from the Earth to a galaxy with a recessional velocity of 150 kilometers per second. Pretty straightforward. D is V over h naught. And I get that. That's 2.08 megaparsecs. Okay, here's example 5. This is the one I was telling you where T is approximately equal to 1 over h naught. This is the example. You need to be able to do this. You need to be able to determine the age of the universe in years. Okay? And I would really recommend that you stop the video before you try this because this is a very, very important problem. Okay, so here we go. So assuming at t equals 0, everything was in the same place. That is to say, d equals 0. The recession velocity would be the separation distance of the universe divided by the age of the universe, right? Because that's just v equals d over t. Now, t is d over v, or 1 over h naught by Hubble's law, okay? So all we got to do is find h naught, okay? And we have to be really careful with our units here, okay? So in this example, I'm using 72 kilometers per second per megaparsec, okay? But you'd get a similar answer if you use, what is it, 67.80, which is what we're using now in the IB, okay? And you get eventually that 1 over h naught is 1.36 times 10 to the 10 Earth years, all right? So this calculation makes a couple of assumptions. Number 1, it assumes that the recessional velocity is constant, and of course it isn't because gravitational attraction has been slowing the rate of expansion, it's thought, okay? Now the universe can't be older than 1.36 times 10 to the 10 years. This is the absolute upper limit. This is the absolute upper limit of the age of the universe by using Hubble's law. Okay? All right, I want to talk a little bit more about the universe, this time the evolution of the universe, which you're responsible for knowing qualitatively about, okay? Now, Newton did a lot of great things, but Newton was also wrong about a lot of things. And one of the things he was wrong about were his notions about the universe, okay? He said or thought that the universe is infinite, okay? Now, if this were true, then everything would be in equilibrium since all gravitational forces would cancel out, okay? So therefore, Newton's idea of the universe was a universe where things were static. So stars have been and always will be in the same places forever, according to Newton's line of thinking. It's also uniform. If it weren't, then forces on every other star would not be balanced and it wouldn't be in equilibrium, all right? Now, Newton's universe, to sum up, is infinitely big, infinitely old, static, and uniform, okay? We now know that none of these are the case. Now, how do we know this, okay? Well, the main problem with Newton's universe is that if it's static, the sky should be infinitely bright because there are an infinite number of stars. It means that anywhere you look in the sky, there should be a star or many stars, okay? Now, clearly it's not infinitely bright. In fact, it's quite dark. It's not, and this is called Olbers Paradox. So therefore, there can't be an infinite number of stars, and therefore the universe itself is not infinite. Infinity doesn't exist anyway. Nothing is infinite. So time is also not infinite, and there's light from stars that, of course, hasn't even reached us yet. So Newton's universe was also debunked because of the redshift from distant galaxies, and of course Newton had no idea about that at the time he was living, nor now because he's dead. More distant galaxies are more redshifted than closer ones because their recessional speeds are less than more distant ones. So the universe is not static, and in fact it's been constantly changing and expanding since its creation. If we go back to that car analogy, the average distance between the cars is increasing, but between them is still the same at all times. It's the same distance, right? It told me that the existence, which makes that distance greater, the existence in which they exist is itself expanding. All right? Okay, a few more interesting things to think about. The universe is also full of structures, lots of things nested inside one another. You can take that however you see fit. Why that is, we don't know. It's just the way it is. But if you look at it at a large scale, there is no structure. Okay? And if you cut the universe into 300 megaparsec cubes, inside each cube looks like any other. All right, and this is called the homogeneity principle. In other words, on a large scale, the universe looks very uniform. And if you look in different directions, you see the same thing. There is no center to the universe, but every point in the universe appears as though it is at the center. So the isotropy principle says that no one direction is any different than any other. If you look in any direction in this night sky or in the sky, you're going to see the same thing. The combination of these two principles is called what's called the cosmological principle, and it basically governs the universe. And the implication is this: the universe has no edge or no center. If it did, it would violate these principles. Okay, so this is a lot of stuff to think about. All right, now scientists agree on how the universe was created. This Big Bang, this thing that happened 13 to 14 billion years ago. But the big question now is what will happen in the future? Will it expand forever or eventually stop? And there are basically three different possibilities. The first is that it's an open universe and it keeps expanding. Note the graph here, which is from your Hamper textbook, all right? The open universe keeps expanding, keeps going on forever. Number two, a flat universe where the rate of expansion goes to 0 at an infinite time. So it approaches, as t goes to infinity, it approaches a horizontal asymptote in this graph. The third possibility is that it's closed. It stops expanding and starts to contract, which means eventually there'll be I guess a big crunch is what it's been called, all right? Now we know that the rate of expansion is not uniform. It is in fact slowing down. But the real question is it slowing down enough to stop? Well, that ends up depending on the density, rho, the density of matter in it. Now, the critical density of the universe is thought to be about 10 to the minus 26 kilograms per cubic meter. What this means is that if the density is greater than that, the expansion will eventually stop. If it's less than that, the expansion will never stop. And of course, we don't know that. We don't know what the density of the universe is, mainly because there's a lot of matter we have not yet discovered. It turns out that about 96% of the universe is thought to be dark matter, right? So 96% of the universe we haven't even discovered. We can't even detect it, right? All the known stars and matter that we can see, that, well, not even that we can see, that we can detect, that we know of, accounts for only 4%. Isn't that amazing? So 96% of it, it's like, well, what is it? Crazy. We can't even detect it, right? And this is where dark matter comes in. And this is matter that does not interact with photons. So we have actually no way of figuring out, of even detecting it or even beginning to figure out what it is. So again, you want to get rich and famous and win a Nobel Prize in astrophysics, you figure out the answers to these questions and you're set. And it would be a really, really amazing acquisition of knowledge for all of humanity.